Well, how about this? Okay, we'll just do one little step at a time. When the remainder of n divided by f is is 0. Does that make any sense to you? Does that make any sense? When the remainder of n divided by f is 0, then f has to be a factor of n. It makes sense, right? Okay, so we'll call it another version. Now we are moving on to version 3. In version 3, we'll basically say, well, can we refine this expression here so that instead of just saying when the remainder of blah, blah, blah is 0, can we use more conventional math notations? So this part relies on the fact that you have read the notes, because I'm going to use an operator that we normally do not use in mathematics. So I would say when n mod f equals to 0. Okay. In normal math, we have multiplication and we have division. But normally, we do not have a mod operator. A mod operator is almost the same as a division. It's almost like a slash, except it does not give you the quotient of the division. It gives you the remainder of the division. Okay? In other words, what is 5 mod 3? 5 mod 3 is 2, because 5 divided by 3 has a remainder of 2. Okay, same way. What is, so I think you guys got the idea of what is a mod operation. It is just like a division, except we don't care about the quotient. We want the remainder of the division. And this is exactly the way it is spelled out in VB and many other languages. You just spell out MOD as the operator, which is kind of odd because it's not a symbol, but most programming languages will recognize MOD as the mod operator. C, on the other hand, uses a percent symbol to represent the mod operator, so it's a little bit different. Okay, well, this is great. Because we are moving along and we are making our algorithm a little bit more like a traditional algorithm with each and every step. Okay, so now, what am I going to do now? Because if the current result, okay, if I give it a certain f, and n mod f is different from 0, that means I have to stay in the loop. But if I stay in the loop and the loop itself is not doing anything, then I'm going to retest using the same f again, which is not going to be very helpful. So what do I need to do to change to a different f? The most intuitive way is just to move it up by 1. In other words, we'll try the next available number to see whether it can be a factor or not. So that means we are going to put f gets f plus 1 here. Okay? Just so that we can move on to the next available number and test that one. Okay? So we'll call this version 4. But version 4 has a very serious problem. It does not say what do we start with. It simply is making a statement and say, as long as f is not a factor yet, add 1 to it and test it again. But what is the first number that we're going to use to test? It does not say. Okay? Okay, let's use 2. In other words, we initialize that before the loop, because we do not want to initialize it in the loop or after the loop. We have to do it before the loop. Okay, that's good. Some people will complain, but this is going to happen first. F gets f plus 1, so by the time we test, f is already 3. But that is not true, because remember, when I use the term loop and loop, I have not specified whether it should be a pre-checking loop or a post-checking loop. So at this point, it is not specified yet, whether it's pre or post-checking. But I would say this loop is looking pretty good right now. It looks like it should work. Okay. So the next thing we have to do in version 6 is to determine, should we should we use a pre-checking loop or should we use a post-checking loop? What do you guys think? Remember what I said? Unless you have a good reason, which one is the usual one? A pre-checking loop is the usual one. So to convert this into a pre-checking loop, it means we have to say while blah 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 do and end while. Now I did not delete the other part because I have to read what condition should I put here. When I say exit when blah blah blah, that makes that condition an exit condition, because when the condition is true, we're getting out of the loop. when we specify while do, we are specifying the condition to stay in the loop. So how are those two conditions related? One is the flip side of the other one. How do you flip a condition? Spell it backwards? No.
It's the opposite.
The opposite? How do we say the opposite?
So it's
Not.
Yeah, so
Okay?
if it's equals 0, then you say it's not true. It's not.
That is correct, but we will say that it is just not the case first, okay? Because I want to just emphasize the fact that all we are doing is negating the condition that we had earlier. Is that okay? So you are already ahead of me. You're already thinking ahead of me. Yep.
Would F have to be, would F still be 2 or would it have to be 1?
Well, I initialize F to 2, so the first number to check is going to be 2.
Okay.
Okay? Yeah. Okay, that's important because otherwise, I would have found 1 to be a factor every single time because every number is wholly divisible by 1. Okay, so we're almost done here. So if anyone is interested, just as he has recommended, we can optimize this code a little bit here. Instead of saying not blah 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 equals 2, we can simply say that it is different from 0. Okay, it's just a slight modification. It does make it a little bit more readable, but it captures exactly the same concept. Okay, are we convinced that this code is pretty close to the logic that we need to find a prime factor of a number? Okay, so the next thing you want to do is to trace it. Give it something. Give it some, easy example to trace. Like 15 would be a good one to try. Use a prime number too. Using this logic here, if I give it a prime number, what is going to happen? If I give it like 7, okay, if n equals 7 before line 1, how many times do we have to go through the loop?
7.
Not exactly 7.
Where-
It's going to be have to go through the loop. The first time is already 2, so it has to go through the loops like this: 2, 3, 4, 5, 6, and 7. So it only has to go through it 6 times because we did not try f equals 1. Okay, but pretty close to the number itself. In other words, if I pick that number earlier, 28 million something, using this logic, it will have to go through 28 million times, more than 28 million times, which is fine for now. Okay, because all we care is that we can do it. So time to trace this algorithm. But I think you guys can trace this algorithm without any problem. So I'm not going to do it in the class. Okay, but you should do it, when you have time. So this is a, do this as an exercise. If you want to just have more opportunities to practice, this would be a good one. And you want to try it with different types of n's. So you want to try it with n equal to, pick something easy first, okay? Pick 4, okay? And then you try something a little bit different. Let's try 9. And you also try it with some prime numbers like 7, okay? So these 3 would be good representative cases as test cases to trace when you work with this algorithm. But I'm not going to go through it, at least not in today's class. If you guys want me to, I can do it, in the next class. But I do want you guys to have a chance to trace it first. It's a very simple algorithm, 4 lines. The only part that is a little bit tricky is, do you remember what mod means? That's basically the only thing that is a little bit tricky about this algorithm. Okay, but here I go. I'm claiming, TAC claims that he can make this algorithm a lot faster without knowing prime numbers ahead of time. Okay? How much faster? It will take only up to the square root of n to determine a number is prime. Okay, in other words, with the number that I randomly picked that turned out to be a prime number, I only have to try some 5,000 and some times instead of 20-something million times. Now that's a lot of saving, okay? That's more saving than knowing the prime numbers ahead of time. Are you guys convinced that, there will be more prime numbers than 5,000 something between 2 and 28 million something. Okay, so how does that work? Yeah, but why does it work? How come I can do something like that? Okay. Prove it. I know it's a good gut feeling. Okay, I know you have a good gut feeling that this has to be true, but can you prove that that is the case? In other words, can someone prove to me that if n has a prime factor other than itself, okay, then either that number or n divided by that number has to be less than or equal to the square root of n. Now, I know I just said a whole bunch of stuff, and you guys cannot keep track of what I just said because I could not either. So let's write it out. Okay, so here's the thing. Okay, just for notation purposes, I pick n to be the product of two numbers. So I pick n to be a times b. Okay, and I claim that I picked a and b such that a has to be greater than 1, b has to be greater than 1. So this is all given to you, by definition of this particular problem. I give you integers. Okay. All are integers. Okay. In other words, we don't have to deal with fractions and irrational numbers and stuff like that. They're all positive integers, counting numbers. Is that okay? So these are assumptions. So my claim, TAC claims that A is less than, the other way to say is A times A is less than or equal to n, or B times B is less than or equal to n. Which is the same thing as saying, the square root of n has to be greater than or equal to at least one of A or B. Are you guys okay so far with that terminology? This is the same as saying, if I want to phrase it in English, this is basically saying the square root of n has to be larger than or equal to at least one of A or B. Okay, it may be A, it may be B. So we'll just pick some numbers. Okay, let's say n equals to 3 times 4, 3 times 5, which is 15, right? So in this case, n equals to 15. The square root of 15 is greater than or equal to 3, which is one of these two numbers, right? Now, but this is only a claim. I have not proved that this has to be the case. I have not proved that regardless of how you take your A and your B, one of them will have to be less than or equal to the square root of n. It makes sense, right? In your mind, you already know that it makes sense. But can you prove it? That's the other question. So in this class, we emphasize on the concept of proving something, because sometimes, when you cannot prove something and you just have a gut feeling, your gut feeling can be wrong sometimes. Yes?
I just had it on the tip of my tongue. B has to be less than or equal to the square root.
Well, one or B, A or B has to be less than or equal to n.
Right.
Okay, they cannot
Because
both be greater than.
Because if they were greater than...
Okay, stop right there. Okay, you just got the proof.